This problem asks us to take the present value of a stream of continuous payments that goes on forever as a perpetuity. The payment rate actually changes over time. During the first 10 periods, it's simply $1, and after that, it changes to 1.03 raised to the t minus 10. For example, at time 10, the payment would be 1.03 to the 0. At time t equals 11, it would be 1.03 to the 1, and so on for any exponent at any point in time. The interest rate is 6%, and they want us to take the total present value of these two streams. We'll start by focusing on the first of the two streams from time 0 to 10. What we're looking at is a single dollar, and at any point in time between 0 and 10, we take the present value at 6%, discounted back a period of x. Now here it's helpful to know a fact about antiderivatives. Whenever you have a function that's of the form a to the x, or to the negative x, then the antiderivative of that is simply negative a to the negative x divided by the natural log of a. And you can see in our case that our a is 1.06. So we'll put that to work for us as we evaluate the integral. What we're left with then is negative 1.06 to the negative x over the natural log of 1.06. We simply followed that formula. We can evaluate this now, and first of all, we can pull that denominator on the outside, 1 over natural log of 1.06. And then first we plug in 10 into the numerator, negative 1.06 to the negative 10th. And then subtract, although the negative turns it into a positive 1 when we plug in 0, since anything raised to the 0 is 1. The total result of that is 7.58. Now we can turn our attention to the second stream. And what we'll do is take a present value at time 10 and then discount the whole thing back. So we start out with a 1.06 to the negative 10. And we're going to carry forward from, even though it's time 10, we'll consider it time 0 to infinity. The payment's 1.03, it's discounted back at 1.06, and we're raising it to the s. Another fact here, similar to the one that we'd learned before, is that the antiderivative of a to the x is going to be a to the x over the natural log of a. Now in this case, our a is 1.03 divided by 1.06. A quick little algebraic note to the side here, that 1.06 to the negative 10th is 0.5584. So we'll carry that through as we work the rest of the problem. So 0.5584, and then as we evaluate from 0 to infinity, we use that fact that we just noted and write down 1.03 divided by 1.06 to the x over the natural log of 1.03 divided by 1.06. Again, we're just following that formula, noting that we have a slightly different a this time. Now here we'll clean things up just a little bit more, noting something about logs. Whenever you have a natural log of a quantity x over a quantity y, it can be rewritten as natural log of x minus natural log of y. And we're going to apply that to the denominator that we currently have in our integral that's remaining. So we're going to actually factor that denominator on the outside and write it as the natural log of 1.03 minus the natural log of 1.06. And then what we have left inside to plug in the 0 and the infinity will be quite simple. It's just going to be that 1.03 divided by 1.06, and first we'll plug in the infinity, raising it to that power. And then subtract off what happens when we plug in 0. 1.03 divided by 1.06 to the 0. And when we raise a fraction that's less than 1 to the power of infinity, it just becomes 0. And anything raised to the 0 power is 1, and we have a negative in front of it. Now we're going to take advantage of that negative sign in front of the 1 and apply it to that constant that's in the front of our expression here. In other words, this denominator, we're going to be able to flip the natural log of 1.06 and the natural log of 1.03 around. Again, we're just taking that negative sign that was in front of that -1 we had determined a moment ago. The result of that is 19.45, and now we're basically done. We can add up these two underlined numbers of 7.58 and 19.45 to get a present value of 27.03, which is the present value that they were asking for in this problem.